Problem number 2.18. An ideal gas of molar mass m, molar mass is given, contains in a very tall vertical cylindrical vessel of uniform gravitational field in which free fall acceleration is given equals to g. Okay, so it is very common thing. The only important point is the gravitational field is assumed to be uniform. Okay, now assuming that the gas temperature is to be the same and that is equals to T. Okay, so this temperature is not changing with the height. Then find the height at which center of gravity of gas is located. Okay, so look, in this question, the very important point is why it is quoting that gravity remains uniform. Okay, because it wants to explore a concept that whenever the gravitational field remains uniform, then for any uniform gravitational field, the center of mass coincide with center of gravity. Okay. So in this question, it is asking for the center of gravity of this gas, which is filled in an infinite length cylinder. Okay. Very long means infinite length. That what would be the position of center of gravity from this point. Okay. So we can simply apply the position of center of mass formula, that is integration r into dm. It will take any small segment dm at any distance r divided by dm, right? Limit would go from 0 to infinite, right? So here we can write dm. What would be the dm? If this height is dr and area of cross section is a and density of gas is rho, right? So we can write dm is equals to rho into a into dr. So we can substitute here. So this h center of mass is 0 to infinite. This is r into rho into a into dr divided by 0 to infinite rho into a into dr. So a is constant, area is not changing, so we can eliminate this term. Okay, now we have to do exercise on this, that how it is changing, right? So here density would change because temperature is constant, but as we move upward, then density of gas will change. For that, we can apply barometric formula, that how density in a gas changes with the variation in height, that is rho equals to rho naught e to power minus mgh over RT, where this m is molar mass of the gas. Okay, so now we can substitute this value in the equation. Then h center of mass is equals to, here we can take r, in fact, if we are taking height r. So integration 0 to infinite r into rho naught e to power minus mgr over rt into dr divided by integration 0 to infinite rho naught e to power minus mgr over rt into dr. So here rho naught is constant, so we can eliminate this term. Now see, in this integration at the numerator, there are two variable functions. One is r dot e to power minus mgr. So we can use integration by parts. You may adopt this formula. First function integration of second function minus differentiation of first function and integration of second function. Okay, so by using this process, okay, in the numerator and denominator there is simple integration. So after solving this, we'll get the position of center of mass as RT over mg, and this is exactly equals to position of center of gravity. So center of gravity would lie at RT over mg, where R is gas constant, T is temperature, m is molar mass, and g is free fall gravitational acceleration.